welcome to my channel. Today I wanted to discuss a very famous problem. This is Alien Dictionary. This is actually commonly asked in interviews. I personally was asked this question in two different companies. One, this was asked in my Evernote interview, which I epically failed. I'll leave a link here. If you haven't seen that interview, I highly suggest you go watch it. And I was asked this on a DoorDash onsite. Let me jump right into this question. There is a new alien language that uses the English alphabet. However, the order of letters is unknown to you. You are given a list of strings, words from the Alien Dictionary. Now it is claimed that the strings and words are sorted lexicographically by the rules of this new language. If this claim is incorrect, and the given arrangement of string and words cannot correspond to any other order of letters, return empty string. Otherwise, return a string of the unique letters in the new alien language sorted in lexicographically increasing order by the new language's rules. If there are multiple solutions, return any of them. This is absolutely a classic topological sort question. Topological sort is basically a modified, specialized version of DFS, which is depth first search. So we've got three examples, and let's go through example 1, and then finally we'll go through example 3. We've got these list of words. We know that they are sorted lexicographically. We are going to analyze every word next to each other, and we can come up with this claim that T, in this case, is greater than F. That means T came before F. Now, if we look at the next set of words, we see that W has to come before E. And in this case, we've got R that comes before T. And finally, we've got E that comes before R. Typically, what you have to do here when you're solving any question that involves the sort of dependency management is you make a dependency map. That map is going to look to represent a DAG, which is a directed acyclic graph, and these are the problems that will require topological sort to answer. So before we get into that, this is the dependency map. As you can see, it's a character key pointing to an array list, or actually I prefer a set of characters that will tell you that the key must come before these values. All right. So this is the pseudocode. We're going to call this for every word that we have in our words list, and we're going to compare the characters of these words. We can add it to our dependency map. After our dependency map, we are going to apply topological sort. I wanted to go over some steps. So number one, it's just DFS. And then the only thing about this is you're going to push every key to a stack after you visit all of its neighboring values. And then finally, we have to reverse the stack to get our topological order. This is the pseudocode that we have here to the right. This is the depth first search. We're going to go through every key in our dependency map, and we're going to call depth first search. We're going to first start with T. We're going to have an empty visited set and an empty stack first. We add T here, and then we check the values of T, and T only has F as its values, so we're going to go through recursion with F. And F here has no membership in the dependency map, so we are simply going to skip this if condition. We're going to push F, so F is going to be the first character in our stack. Finally, we're going to come back out of the recursion, and we are going to add T to our stack. Now, we're going to go into our next key, which is W, and W is going to be added to the visited set, and we're going to go into recursion here. W's child is E, so we're going to go into E. E is going to be added to the visited set, and E is going to go into R, so we're going to go into recursion with R, and we're adding R to the visited set, and R has the value T, And if you recall, we've already visited t in our first iteration, so we're going to return true. And then finally, we're going to add to the stack. We're adding r to the stack. And now we come out of our recursion, and we are going to add e into our stack. And then finally, we're back to w. W is done. We're going to add w to our stack. And that's it, you guys. We just finished traversing all the keys in our dependency map. We finally have our stack reading like this. And if you recall, our very last step is to reverse the stack, to pop out of the stack so that you can get the topological sort order that is going to yield us this answer. For example 1, this is essentially how you perform topological sort. We have a couple things to worry about. There are straggler characters. If we added an extra character b, let's say we have this example with b never makes it to the dependency map here. So how do we accommodate for characters that may not make it to the dependency map? All we need to do is add all the characters that we're ever dealing with to an all set. And you can really easily do this by traversing through every word. Once you have your all set with you, you just need to take a diff of the all set with the keys and the values in the dependency map, and you will get your list of straggler characters. And once you have that list with you, you can put it at the very end, you could put it in the beginning, or you could even put it anywhere else. It really doesn't matter. Cyclic dependencies. This is the last thing we need to worry about. This brings us to example 3, which gives us an example of a contradiction. So if you look at this closely, basically we're saying z comes before x, but x comes before z, which doesn't make any sense. And topological sort is not going to work on these examples. We need to somehow find out about these cycles. And if you think a little bit deeply, you'll see that we can actually do this by introducing a little if statement check here. If key is in a visited set, but if the key is not in a stack, that means we're in a cycle. Really think about this. It's really imperative that you understand this. And if you do detect that cycle, you simply opt out of the recursion by just returning false. And you propagate that false value all the way up. And you just return an empty string as the problem wants you to. And that's really all it is, you guys. This is really all you need. I will show you the code and compile it for you. This is essentially everything we've already discussed. There's nothing new here. So we've got the dependency map here. We're constructing it. We have our process. And the concept is really all the same. Like, we've added the all set here that eventually we're going to diff in order to get our stragglers. And we are iterating through our DFS search here. And our DFS search looks exactly like what we discussed. I'm going to go ahead and submit this code, and voila, our runtime is 100%.